this is going to be all about matrices. This whole chapter is about matrices. In section 8.1 relates to how matrices and systems of equations are related. Okay. Before we get into talking about systems at all, just a few housekeeping things to remind you. If we have a matrix, and if we say a matrix is m by n, like 3 by 4, 10 by 5, whatever it is, that means that it has m rows and n columns. So, we put our square brackets around it, and then there are m rows, and there are n columns in our matrix. Okay. And m by n, this is called the order of the matrix. And so if, in just a special case, if m equals n, then the matrix is said to be square, because it'll make a square shape if there are the same number of rows and columns. And each entry in the matrix is denoted with a subscript. So if this is matrix A, we use capital letters to denote matrices. Each of these entries are called little a with subscripts. A11 means the entry in row 1, column 1. There we go. A12 means the entry in row 1, column 2. Whoops, sorry. This A12. A21 would mean the entry in row 2, column 1, and so on and so forth. All the way over here we'll have A1n, because it is in the nth column. And then all the way down here we would have AM1, because it's in the nth row, or the mth row. And all the way in the corner we wind up having our AMN, because it is in the nth row and nth column. So that's how we denote matrices in the various entries in a matrix. Matrices are very related to systems of equations. When we were solving systems of equations, we used a process called Gaussian elimination. Although, to be 100% accurate, we didn't do the whole process. The whole process is really a matrix operation, and it involves generating a matrix that has zeros, all zeros below the diagonal, and all ones on the diagonal, and then you can have whatever you want out in this upper right portion. So when you're doing Gaussian elimination, the goal is to get a matrix that has all zeros below the diagonal, all ones on the diagonal, and other stuff up here. And then when a matrix is in that format, it is said to be in row echelon form. And you're going to need to know that term, because if I say put a matrix into row echelon form, you need to know what that means. That means you should use Gaussian elimination. Okay? And we can perform what are called elementary row operations in much the same way that we add equations or multiply them by a constant or whatever when we're solving a system of equations. Those elementary row operations are just multiplying by a constant or adding multiples of the rows together. So let's take an example. Let's say we have a matrix. And I'm just going to make up random entries. All right, let's say this is our matrix. And I'm going to go through the elementary row operations to put this matrix into row echelon form, which is very similar to what we do when we solve the system. Another elementary row operation we can do is switching rows. And because I already have a 1 here, and that'll make it easier to eliminate values, that's the first thing I'm going to do, is I'm going to swap row 1 and row 2. And this is, the way I'm showing this is the way I'm going to want you to show your work as well. So I'm going to change what the matrix is, and I'm going to do that by swapping rows 1 and 2. Okay? So then, I can write my new matrix just with those rows swapped. That is an elementary row operation. Then, as I said, we can multiply rows by constants and add them together. So I want to, we need to have zeros below the diagonal. So I want to get rid of this 4, and I can do that by taking minus 4 times row 1 and adding that to row 2. So if I do that, my row 1 stays the same. My row 2, negative 4 plus 4, becomes 0, which is what we're aiming for, so that's good. Negative 12 plus 2 is negative 10. Then we have negative 20 plus 6 is negative 14. All right. I'm also going to want to get a 0 here, and so I can do that in the same step to save myself some writing. I also want to take negative 3 times row 1 plus row 3, and that will make a 0 down here. So this becomes 0. It's negative 9 plus negative 7. Or plus positive 7, sorry, which is negative 2. And then negative 15 plus 4 is negative 11. All right. Now also, in order for a matrix to be in row echelon form, we need to have 1s on the diagonal. So here, I have a negative 10, and I want to make that a 1. Now it's your choice. You can do that at this step, or you could do it after this step. I think it's easiest just to. So it depends on what the matrix looks like. Right now, I know I want to make this a 0 eventually, because I need to have zeros below the diagonal in order for it to be in row echelon form. And since I want this to be a 0, I want these two to be easy multiples of each other. Since 10 and 2 are already easy multiples of each other, I'm going to go ahead and eliminate this first. If I could make this a 1 and this wouldn't be a fraction, then I would go ahead and do it. Or if this was like 9 and 2 and I'd have to do more involved multiplication to get it there, then I would do it that way. But you can either make all zeros first and then make 1s, or you can make 1s as you work your way down. It doesn't really matter. All right. So what I'm going to do, I want to eliminate that negative 2, and to do that, I can take row 2 minus 5 times row 3. So row 1 remains the same. Row 2 remains the same, but then we replace row 3 with the result of this. Well, 0 minus 5 times 0 is still 0. Negative 10 minus 5 times negative 2 is negative 10 plus 10, which is 0. That's good. And then we have negative 14 plus 55, which gives us 41. All right. And then our last step to put this into row echelon form is that we need to have 1s on the diagonal. So in order to get 1s on the diagonal, I need to take row 2 and I need to divide it by negative 10. And I also need to take row 3 and divide it by 41, which might be troublesome if we had any other entries in that row other than the 41. But dividing 40, since there are no other entries, it's not a problem. Row 1 remains the same. We haven't done any operations to row 1. We divide row 2 by negative 10. 0 remains 0. Negative 10 divided by negative 10 is 1. Negative 14 divided by negative 10 is 14 over 10, which is 7 over 5, which you could write, or 1.4, depending on what floats your boat. I would say 7 over 5 because I like fractions, but if you wrote 1.4, that would be fine. These two remain zeros, and then 41 divided by 41 is 1. And now this matrix is in row echelon form. It has zeros below the diagonal. It has 1s along the diagonal. Right? Now I'm going to go ahead and do an example that has a non-square matrix. So if we're solving a system of equations, chances are we're going to be dealing with a square matrix. We'll have the same number of equations as variables, but for a matrix, it doesn't have to be square to be in row echelon form. Let's say we have this matrix, and I'm just making these entries up. There's nothing particularly special about them. Say we have this. It only has 2 rows. So when I say there have to be 1s down the diagonal, what I'm really talking about, it's not really it's not going to be the diagonal of this matrix, because if you drew a diagonal, it'd be kind of across here. But when I talk about 1s on the diagonal, what I'm referring to are what are called the main diagonal entries, which are A11, A22, A33, etc. The ones that are in the same row as column. So in this case, row 1, column 1 is talking about this 2. Row 2, column 2 is talking about this spot. So those are the entries that I'm going to want to be 1. Everything below that diagonal, that's just this entry, we want to be 0. Okay. So first step, turn this 3 into a 0. And we can do that by taking 3 times row 1 minus 2 times row 2. Row 1 remains the same. 6 minus 6 is 0. 12 minus 10 is 2. 3 minus 0 is 3. 21 minus 2 is 19. And then I need to have 1s in these diagonal entries. And in order to have 1s in these diagonal entries, I simply need to divide both of those rows by 2. So I'm going to take row 1 divided by 2 and take row 2 divided by 2. And so I get 1, 4 divided by 2 is 2, 1 half, 7 halves, 0, 1, 3 halves, 19 halves. And this is my matrix in row echelon form.